In today's lesson, we're going to talk about two different topics. The first and longer topic will be factors affecting the solubility of substances. And then secondly, we'll talk about the rate of dissolving, which is dealing with how fast or slow something would dissolve, most likely in water. When we talk about solubility, by definition, it states that solubility is whether or not a solute will dissolve in a solvent, and then the extent in which it will dissolve. And this can only happen at certain conditions. So this usually is at a certain temperature, certain pressure, but we are talking about whether a solute will or will not dissolve in a type of solvent. So whether a solute will or will not dissolve in a solvent is based on three factors. The first is the nature of the solute and the solvent. And this is going to go back to Unit 1 when we discussed polarity and the attractions or intermolecular forces and the attraction between solute and solvent. So we'll be reviewing that. Another factor that affects solubility is temperature. So not all substances will dissolve whether the temperature of your solvent is hot or cold. And then lastly is pressure. This is only applicable to gases, and we'll discuss how pressure affects the solubility of them. So let's talk about the nature of solute and solvent first. When we discuss this, we need to remember the difference between covalent and ionic compounds and whether these compounds are polar or non-polar. So recall that a polar solvent will be a liquid made up of polar molecules. So for example, we know that water is polar. If we come down to this diagram, here is a little ball and stick model, we would call it, of a water molecule. And you'll see a negative end and a positive end. We typically draw a dipole through, so let me do it over here instead. We draw a dipole through our water molecule, and we show that the one end is slightly negative, the other one is slightly positive in terms of its charge. So we need to revisit polarity, and if possible, you might want to review those notes because that is going to be used to explain whether something will or will not dissolve. Similarly, you're going to need to know whether a substance is nonpolar. So if we have a nonpolar solvent, recall that the molecule will be symmetrical in terms of the electronegativity and the distribution of electrons throughout that molecule. So ethane here is an example of a nonpolar molecule. When you write out ethane structure, which looks something like this, when we have two carbons bonded together, we know that the difference in electronegativity between these two carbons will be 0. And anything that is bonded to carbon and hydrogen has a difference in electronegativity of 0.35. So what we know is that over here on this molecule, we don't have any electrons being pulled towards carbons or hydrogens. So overall, it is a nonpolar molecule. And in this case, ethane would be a nonpolar solvent. So how does knowing the nature of solute and solvent predict solubility? So when two substances are similar in terms of their polarity, they can dissolve in each other. So polar solutes will dissolve polar solvents. If you have a nonpolar solute, it will also dissolve nonpolar solvents. So we use this phrase like dissolves like in order to recall that. If you have a molecule that is polar and has charged ends on it, it will be able to attract other charged ends of the molecule. If you have a nonpolar substance that has no charged ends, they'll be able to attract the other molecules through London dispersion forces, which we saw when we talked about IMFs. If you have an ionic substances have charges, right? So they have charged ions. And so as a result, they will be able to dissolve or be soluble in a polar solvent because polar molecules have charged ends. Not fully charged like an ionic, but charged enough that they will be able to attract these ionic charges of those ions and be able to dissolve. If you have a nonpolar solvent that has no charges on it, you cannot attract those charged ions. So here's an example of how we show whether ions or polar molecules or nonpolar molecules would attract each other. Here's an example here of sodium chloride, which is salt, and how it dissolves in water. And when we look here, we see that the sodium ion here has a positive charge on it. What it will do is it will attract the negative end of your water molecule. So we're not showing the charges here, but we can. There are the partial charges on your water molecules. And so all the negative ends will attract that positive cation of sodium. And this is how things are attracted and then dissolve. Similarly, the negative anion of the chloride ion will attract the positive end of the water molecules, and we get these electrostatic attractions happening. So positives and negatives attracting each other in all of these directions. This is called ion dipole attraction. Okay, and that makes sense because you've got an ion, charged ion, and you got a dipole on a polar molecule, and like dissolves like. Over here on this molecule, we have two polar substances. So let's draw in the dipoles here. So water, the negative end is always the oxygen molecule. And the other molecule that here is called ethanol. And ethanol right here will be nonpolar, similar to that ethane molecule we just saw. But over here, we would have electrons being pulled towards our oxygen, and we would have a dipole through this little part of the molecule. And this is where you get this attraction between positives and negatives. You also get hydrogen bonding here. Okay, so be aware of all these things that we learned with IMFs. You'd have dipole-dipole attraction. And in this case, you also have hydrogen bonding. So if needed, make sure that you go back and review those. Here's a chart that summarizes the attractions between solute and solvent. So again, like dissolves like. If you have a polar or ionic substance, it will also be soluble in another polar substance. Nonpolars will be soluble or attracted to each other. If they are nonpolar or polar and ionic, they will not be attracted to each other. Now let's switch and talk about temperature as a factor for solubility. So temperature is, heating up or cooling down your solvent to see if the solute will dissolve better. So the solubility of solids and liquids tends to increase as the temperature increases. And the reason for this is that your solvent molecule, so think of water, will have greater kinetic energy. They'll be able to move around faster. They'll be able to collide with more solute particles and be attracted to them a little bit faster. For liquids, so if you had a liquid solute and a liquid solvent, because they're both at the same temperature, there is little energy exchanged. And so this really has no effect. Okay, so we should be aware of that. The temperature isn't always going to increase the solubility of something. And then with gases, temperature actually has the opposite effect. So as the temperature increases, the solubility of a gas actually decreases. And this is an important one to know, and we'll explain it here by talking about the pressure that needs to be applied here to gases to make it soluble. So remember one thing here, that gases are most often, I feel like 99% of the time, they are non-polar substances. Okay, and if you're trying to dissolve a gas in water, it doesn't want to dissolve because of the nature of the two of them. It's a non-polar gas, polar liquid. They're not attracted to each other. And so what we do is we tend to apply pressure and force that gas into the solvent. Okay, think of a carbonated beverage. So a can of pop, for example, The minute you open up the pop can or untwist the cap of a bottle, you hear the gas escape. And we know that it was pressurized prior to that to force the gas molecules in. If you increase the temperature, you actually are going to increase the kinetic energy of those solute gas molecules, and you're actually giving them more energy to get out of solution rather than being forced inside. This is why we tend to cool down carbonated beverages or cool down solutions that include gases in order to allow them to dissolve a little bit better. When they have less kinetic energy, they're more apt to stay put in solution than try to escape it. Here's a great little video on polarity of water molecules. So stop the video and go over to Google Classroom and you can play this video as a bit of a break. Now let's talk about 3 factors that affect dissolving. So this is an important distinction between the previous lesson. What we're doing here is we are assuming that our substance already is going to be dissolved. Okay, so we're assuming that sugar does dissolve in water, salt does dissolve in water. These will be factors that affect how much faster can we get them to dissolve. So there are 3 factors that affect rate of dissolving, okay? And rate just refers to, how fast, okay? So how fast we can get something to dissolve. The first one is surface area, the second is agitation, and then the third is temperature. And our second point says that the rate of dissolving is unrelated to solubility. So if something is not going to dissolve in a solvent, you can change the surface area all you want. You can agitate or stir it all you want. It will never dissolve. Okay, so these factors only affect solutes that already will dissolve in a solvent. When we talk about surface area, we can speed up the rate of dissolving by increasing the surface area. And what this means is breaking up the solute particles into smaller bits that can now be more exposed to your solvent. So I think of, if this is sugar, for example, like a sugar cube versus granulated sugar. The sugar cube can only access the water molecules from the outside here. Okay, so there you'd have solute-solvent interaction just on the outside of the cube, and you'd have all these particles on the inside not interacting with solvent. If you crush that up and you have granulated crystals like we see over here, all those little crystals can interact with water at the same time. Agitation is when we stir or shake up a solute-solvent solution. So when we do this, we bring fresh solvent particles in contact with undissolved solute particles, and this will allow solute particles to dissolve faster. And lastly, if we increase the temperature, so again, assuming that something will dissolve, we'll give more kinetic energy to those solvent particles, allow them to move around faster, and then they will interact with your solute that much quicker and interact them and attract them and dissolve them that much quicker as well. Remember that this will not affect liquids or gases.